Hello, good afternoon. So first, an announcement. I was asked to tell you that the data that you have on the servers at the Institute is not going to be accessible from the outside the Institute. So once you leave, the data will disappear. So you better download the data before you leave if you actually want to have access to it later. Okay? So today's last session is today's speaker is Kevin Bowers, who we're very fortunate to have. Kevin is working at D.E. Shaw Research, where he's designed, built, and optimized a molecular dynamics package, Desmond, which is an extremely capable tool for numerical biology simulations and other things. But in his spare time, Kevin is also a guest scientist at Los Alamos National Laboratory, where he has developed the fastest particle and cell method in the world, the most optimized and coolest and most capable particle and cell method. So this code called VPIC, and which has recently breached like almost half a teraflop. Half a petaflop on a, bit of a difference. Half a petaflop on the fastest machine in the world, the Roadrunner machine. So the theme of this meeting, this school was not only how to write codes, but also how to use them and how to optimize them. And I think we're very fortunate to have Kevin talk about how to squeeze that performance out of the latest generation of petaflop machines. So Kevin.
Thanks, Anatoly. So can everyone hear me? Yeah, okay, I guess I'm amped up now. Okay, so the title of this talk is Petascale Kinetic Plasma Simulation with VPIC and Roadrunner. As mentioned, I'm Kevin Bowers. This work was done in collaboration with Brian Albright, Lin Yin, Bill Doughton, Vadim Reitershetten, Ben Bergen, and Tom Kwan of Los Alamos National Lab. As noted, I'm technically a guest scientist. This is just have strange hobbies. So I was already asked to give this talk at PPPL, so if you were there, you'll recognize a lot of these slides, and this will basically cover a lot of what I covered there. And indeed, what I'll be covering here can be broken down into the three S's. We have the software, the supercomputer, and the science. The software is VPIC, which is a three-dimensional electromagnetic relativistic particle and cell simulation code. The supercomputer is Roadrunner, which is a petascale heterogeneous cell opteron cluster. And the science I'll talk about is laser plasma interaction, inertial confinement fusion, laser ion acceleration. And in the original version of this talk, there were some slides of magnetic reconnection, but I noticed Anatoly in his slides already covered that. So instead, we'll have a photo gallery of all sorts of pretty three-dimensional magnetic reconnection simulations that we've done, but I won't talk about them so much. For the PPL talk, I did have some slides on how to accelerate existing gyrokinetic PIC codes. And even if you're not interested in gyrokinetic PIC codes, some of the considerations that go into designing optimal methods might be useful, so I'll probably touch over them as well in place of magnetic reconnection. But before I get into that, first I'll preach to the choir, which is that we already have petaflops computers today, one being Roadrunner, another one being Jaguar at Oak Ridge. And we know with the trends in Moore's law that exaflops is likely to occur within 10 years. At the same time, if we look in most fields of science, there is very few observational or experimental capabilities that will see a 1,000-fold increase. And this means that we are well positioned to make great discoveries in biology, chemistry, climate, cosmology, energy, materials, plasmas, and so forth. But before we can realize this power, we need to recognize a couple things about modern computers. The first is that they aren't designed for high-performance scientific computing. Modern CPUs are optimized for games. And if we look at a video game uses floating-point intensive, small matrix short vector operations in single precision. As a result, when you look on these processors, they support SIMD, but it's usually single precision SIMD. It's usually 4 vectors. It's hard to get double precision to run at full performance on this. So if you're running a traditional legacy style code, for example, maybe written in Fortran, maybe based around large vector type operations, it won't be very efficient on a modern computer. In fact, if you look at Roadrunner, Roadrunner is based around a chip originally designed for the Sony PlayStation 3 video game console. The next thing we need to recognize is that the speed of light is way too slow. And the way to understand this is if you open up your computer or workstation, you'll find chips that look like this. This is a memory DIMM. You can buy these at Best Buy. They're about 3 centimeters wide. They're about 13 centimeters long. And if you just think, how long does it take, say, for a signal to come in here, get some data maybe off here, do its parity checks, basically propagate around this chip? How long does it take for light to do that? Again, taking into account that you're in a medium which is half air, half printed circuit board, silicon dielectric, whatever. You're going to find that the characteristic speed of light for the time for the propagate around this is about 3.2 nanoseconds. Now, in 3.2 nanoseconds on a modern chip, for example, like the chips used in Roadrunner, which is at 3.2 gigahertz, and it can do 8 4-vector operations every clock cycle, that means that in that 3.2 nanoseconds, you could have got 80 floating point operations done. And I'm being very optimistic here. There are many other delays in practice when you actually want to recognize this. So what we find is that due to physical limitations, moving data between and even within modern microchips is more consuming than performing actual computations. Another thing we need to recognize is that we are still smarter than the compiler. Languages are a lot more restrictive than people expect. For example, if I'm programming in C and I write this operation right here, the compiler cannot turn it into this operation. This looks pretty simple, but it can't. And the reason why it can't is that floating point addition is not associative. And so it's actually very good the compiler doesn't do it. And when compilers do, I actually get very angry. But if the compiler is getting hung up on this level, it's kind of unrealistic to expect it to say, oh, it looks like you're writing a relativistic magnetohydrodynamic simulation. Here, let me redo that for you. For example, to give another one, and if you can figure out why this example works, I'll want to talk to you about a job. In any case, if I look at this loop, if I'm in C and I index a loop Fortran style from 1 to n, for example, I might be doing x plus equals v times delta t, a common integrator operation. If I write the loop this way, the compiler cannot safely unroll it, pipeline it, and do all the other transformations that you would expect it to be able to do. However, if I write it a more conventional way down here, from indexing from 0, it can. And this is, again, due to some technical limitations of the language. The main point is the compiler and languages and whatnot do not expose the limitations, capabilities that you find in high-performance computing. They just don't have the context to understand what you're doing and do a good job of optimizing. So as a computational scientist, we still need to know something about the computational side of things. An unfortunate side effect of this, or maybe not a side effect, but an unfortunate aspect of this is that this situation, I think, is very unlikely to improve. Part of the reason is that most computational scientists don't really know these level of details to make their codes run fast. And even if they did, the compiler writers are unlikely to write their compilers in order to exploit them. And that's because high-performance computing is a moving target niche. Right now, we're in a time of upheaval in high performance. We're going from essentially large clusters to these GPU-enabled hybrid architectures and so forth. Likewise, in the past, there was a transition from large vector machines into clusters of commodity software. And so they're not going to spend all the manpower to develop for a platform that they don't know if it will be there in the long term, and if they don't have users who actually know what to do with the capability anyway. So to get into the software now, I'll talk about VPIC. We'll talk about the modeling capabilities that it has. We'll compare it with other techniques that are used for integrating the Boltzmann equation, and then give some implementation considerations. So what does VPIC do? Well, VPIC integrates the relativistic Maxwell-Boltzmann system in a linear background medium for multiple particle species. So up here we have the Boltzmann equation, here we have the Maxwell equations. It uses an explicit-implicit mixture of velocity relay, leapfrog, Boris rotation, exponential differencing that is based on a reversible phase-based volume-conserving phase-based volume-conserving second-order Trotter factorization. Of course, directly discretizing this can be prohibitive if you're doing the full 6 dimensions, the 3 dimensions of space and 3 dimensions of velocity of this equation. So we actually sample by particles that follow the characteristics of Boltzmann's equation. These computational particles have the same Boltzmann equation outside of collisions, but we need to handle collisions separately because of collision effects, and I know Anatoly covered that a little bit in his talks. And then in practice, we extrapolate a smooth J, and because of Nyquist's theorem, we know that if J is smooth, we can sample it on a mesh, and we can interpolate that back and forth to the particles. But this exploitation is mostly useful for making babies cry, although with this audience, there's enough people here who would actually get this explanation. So if you want, we can go in, particularly at the end, a lot more details on the numerical methods that are used in VPIC. So what does VPIC really do? And this will get into what goes on under the hood computationally with VPIC. Well, first, PIC, it stands for particle and cell. And in this talk, instead of saying the word cell, I'll say the word voxel here to disambiguate from the cell processor that's used in Roadrunner. And over here we see a cell, we have a particle, it has a position, it has a momentum, and before we can do anything to that particle, we need to read it in. And in VPIC, this costs 32 bytes of data traffic. After we read it in, we need to figure out what fields are acting at that particular particle. So we take its position and we load in some fields from the cell or voxel in which it's contained. We do some math and we come up with the electric and magnetic fields that are operating on that particle. This takes 72 bytes of memory traffic, and we do about 27 floating point operations to produce the electric and magnetic fields. Based on that, we can do a lot of crunching. We have all the data we need, and about 107 flops later, we know what the new momentum of that particle should be. This is basically just integrating the Lorentz equation. And then we're going to compute the motion of the particle. Now in VPIC, this takes 48 bytes of reading and writing and 70 flops, and this is written this way because VPIC actually has a short circuit here depending on whether or not the motion was simple or complex. You see, in VPIC, we just can't pick up the particle and put it down where it landed. Instead, what we need to do is we need to walk it across the mesh, taking into account the current produced by the particle as it moved. So first, we will take the particle, we know it should end up here, and we'll push it to the edge of the voxel in which it's staying, and we'll read its fields, or sorry, we'll read the currents and we'll write the currents, accumulating the particle's influence as it goes. And then we'll do it again for the next cell, and we'll do it again for the next cell. And then after we're done, we'll have our new particle updated. Overall, what we find is that we've done about 232 floating point operations, plus some extra depending on how many voxels we cross through, and we've done a comparable number of computational bytes, of floating point operations to follow. Why would you do this? Well, Vlasov codes model similar equations, but they don't scale to higher dimensional systems. Traditional Monte Carlo codes are easier to parallelize and accelerate, but they aren't suitable for time-dependent effects, and most of our users are very interested in non-equilibrium and time-dependent effects. Computational fluid dynamics is a far cheaper way to go than PIC, and if you have an equation of state that you trust, I recommend using it. Unfortunately, for a lot of simulations in relativistic plasma physics or in other areas of plasma physics, the equation of state is not known or not terribly well trusted. Molecular dynamics is the most closely related technique to it, but it's actually orders of magnitude even more expensive than PIC. And to understand this, we can first look at MD, and MD, the focus is on the short range. And this is necessary because in the typical regimes in which molecular dynamic simulations are used, the interaction potential energy is far greater than the thermal energy between the particles. As a result, it's very difficult for the particles to represent many atoms. You have to take into account the detailed impact of collisions and so forth going on. The flip side of this is that you end up doing a lot of operations per particle per step. If I look at, say, the MD code I developed in my day job, you're looking at about 1,000 to 10,000 floating point operations per particle per step. In PIC, the focus is on the long range, and this is kind of textbook here, but plasmas are when the nearby interaction potential energy is much less than thermal energy. As a result, collective effects dominate. We can approximate the effect of collisions. We can use macroparticles, and this is very good. It allows us to get the bigger domains, a cheaper computational cost. It also means that the number of flops per particle per step is much smaller. Now, this is good from an algorithmic standpoint. We're doing less work and we're getting more done, provided we can make this approximation within our code. But it's also bad because computers are really bad at moving data around, and if we're not doing a whole lot with the data we have, we're going to have trouble getting high performance. And to understand this better, let's look at what a typical VPIC simulation. First, we typically have many particles per node, and this will be on the order of 10 to 100 million particles. As a result, particle data can't fit in any level of the cache hierarchy that exists within memory, and over 90% of the expense in VPIC is spent pushing around particles, doing that integration I showed before. There are also many voxels per node, and this is on the order of 10,000 to 100,000 or so. And as a result, none of the field data can fit in any level of the cache as well, and a simple division says typically people are running 100 to 10,000 particles per voxel for these simulations, depending on how much phase space resolution they need for their phenomenon of interest. So these are generally pretty bad because it means there's a lot of data. There are some good things, though, which is that VPIC is an electromagnetic code. Being an electromagnetic code, there's very few voxel boundaries crossed per particle per step. And that's because we need to resolve the speed of light, and particles, by necessity, are moving slower than the speed of light. And also, again, because we're an electromagnetic code and everything is local in electromagnetic code, our internode communication is naturally optimized by a spatial domain decomposition. So even though we need to communicate every step, we don't need to do anything nasty like a big solve of Poisson's equation where all the nodes need to communicate, and thus limiting your scalability. So at least for weakly scaling problems, where weakly scaling means we just do bigger problems on bigger supercomputers, an electromagnetic, relativistic, purely local codes can essentially scale until you run out of money, as opposed to run out of algorithms or run out of communication or whatever. But one thing to take away from this is that also VPIC is not like a matrix calculation where you're doing a lot of compute on a limited amount of data, and as a result, you can get high performance. And because we're doing a low compute to data motion ratio, and what we saw before is about a flop per byte, it's really hard to achieve high performance on these modern processors, which are so limited by memory bandwidth. Our performance is limited by local data motion. So to get an idea even better as to what's going on, this is actually a benchmark I did about 3 years ago, and it's worse nowadays. But this is the cost for various types of operations that you might build your scientific code out of. So these are very low level, but at the lowest here, we have a floating point operation. And a floating point operation takes about 1/10 of a nanosecond. And then we can talk about how much does it cost, what's the marginal cost of moving around data. So if I want to load an extra word, a 32-bit word out of memory, or a single number, for instance, if I need to load it and it's already local to the processor in its cache, that might also take me 1/10 of a nanosecond. But this gets worse and worse as we go further and further out, where if I need to actually access those memory chips, this is on the order of a marginal cost of about 1/2 a nanosecond. But data movement isn't so bad. This one is essentially how many wires are going into your chip. The real problem here is latency, and latency gets really bad really fast. Even to talk to the L1 cache within your chip, you're looking at about 1 nanosecond cost. And to talk to another processor on a different node, you're looking at about 10 microseconds worth of cost. So if you're thinking of saying MPI underscore anything in your code, it better be worth 100,000 floating point operations to you. Otherwise, it's worthwhile to replicate that computation or find some other way to get around it. Sorry, what? Because the speed of light's not getting faster, but computers are. So as things go forward in time, they're giving you more and more floating point units on the chip, but the memory is still the same distance away, and it's hard to keep these guys fed. So, well, yeah, latency, but a component of latency is speed of light. But there's certainly other components in there, but you won't. I mean, even speed of light as a consideration by itself is pretty large. It's actually not the dominant consideration, but the main thing to take away is that those numbers. If you look at it going forward in trends in commodity computing, what you'll find is that it's easy to throw down lots of transistors. Moore's law means lots of transistors are appearing on the chip. They can give you lots of multipliers to use to do neat things with. But feeding those multipliers is difficult. It's really difficult to bring wires into your chip because you run into signal issues, you run into packaging issues. It's a combination, that one, of a physics and economics problem. I mean, if you have enough money, you can buy more bandwidth to feed your chip. But the one that you really can't get around very effectively is latency, which is that if you're talking to a node, say you have a big supercomputer, it's in a rack, you have another node that's 10 meters away. Well, you're 10 meters away at the speed of light for that data to get to your computer. And so doing tightly coupled latency, that's just not going to improve. Or at least it's going to improve at a rate slower than you see the rate of improvement on things like compute and bandwidth. So if you look at, and were to implement a PIC code using traditional, just kind of looking like Birdsall and Langdon, or look at some of the classic codes that have been used, a lot of the naive ways of implementing a code are ways that worked very efficiently on older vector supercomputers like a Cray XMP or so forth. You'll find a lot of ideas that are bad ideas now. The first being absolute position coordinates. And this is bad because it destroys it destroys the precision of your code. You end up wasting a lot of bits resolving voxel indices. It's also bad because you have to do a lot of operations in order to figure out what your fields are at the particle. The position comes in, and you need to do a lot of math to figure out exactly how is this guy positioned within the voxel, and then translating that into the interpolation scheme to get your fields. Another thing is that if you don't take any effort to make your particles organized, if they're unorganized as your processor is processing through the particles, it's having to hop all over memory to bring in field data in order to do its particle advance. You have lots of cache misses, and then those hierarchies, which we saw had faster performance, aren't helping you anymore. Likewise, something which is somewhat contrary to what you might want to do from a software engineering standpoint, if you were to write your code to do the advance in several passes, you end up wasting a lot of bandwidth, which is a scarce resource nowadays. By doing your advance in several passes, I mean, you might say, here is my loop which does the interpolation of the electric field, here is my loop which does a Boris rotation to do the magnetic field integration, here's my loop which moves the particle position, and do those in separate passes. You do that, you can write nice, very elegant operations. Unfortunately, it's very slow because you're limited to by how many times are you pulling the particle data to and from memory, and you end up wasting that bandwidth because you're touching your particle data several times per step. Likewise, if you were to store each component of your particle and your field in a separate way, you're making your life really hard on your processor, and this is because instead of going and saying, I want this particle bringing that data in one big chunk, You're saying, I want the X component here, and I want the Y component here, and I want the EX and the EY components from all these different areas. And it becomes lots of small unaligned accesses. And about the only thing modern processors are good at in terms of bandwidth is doing huge block transfers of data into your processor. Likewise, if you use the field samples directly for your interpolation, now in addition to having to go to different areas of memory for your EX and EY and EZ, within those arrays you're having to hop around X strides, Y strides, and Z strides. In fact, if I go through the numerics of VPIC and I say, if I was to do a conventional implementation of it, how many different memory regions do I access? I do about 29 different memory regions accessed per particle. And caches aren't that smart. Caches can only really keep track of maybe 3, 4 different regions of memories being accessed at the same time. And so if you throw 29 at it, the cache essentially does not have enough intelligence to keep up with what you're trying to do, and it won't be that effective. So if I actually go through that and then say how many of those memory regions translate into DRAM transfers on a conventional implementation, there's about 31 physical DRAM transfers per particle per step, and there's not a whole lot of flops to show for these. And so what we really need on modern codes are data flow optimization techniques. And one main point here is that scientific codes, when they're often written, particularly the first time, if they're not written with this in mind, they will use data structures that are easy to implement quickly, but that will limit your flexibility, your scalability in the long run. So every one of these ideas in VPIC is replaced with a better idea. First, we use voxel index and offset particle coordinates, and this maximizes precision. And this is especially critical if we want to exploit the single precision capabilities of modern processors. It also means that we can do our interpolation very fast because our particle positions are already stored in a format which is amenable to doing interpolations using your field data. Likewise, we sort the particles. There are many good algorithms for sorting the particles very efficiently. As a result, when we're passing through the particles, our field data is being approximately accessed sequentially from memory. We also do the advance in a single pass, so we have essentially a monolithic particle advance loop which does everything from the field interpolation to the magnetic field rotation to the placing of the particles to the interpolating the current from it. And this is nice because we only touch the particle once per step. As a result, we end up maximizing our potential gain, or using the bandwidth as efficiently as possible that's given to us. Lastly, not lastly, but we also group similar components together. So our particles are stored contiguously within memory. As a result, when we get particle data, it comes in a big, large aligned access, and likewise, we do that for the field data structures. In fact, we go a step further with the field data structures, which is that for the field data structures, instead of using the fields directly, we pre-compute an array of voxel interpolation coefficients. So as a result, if we actually go through VPIC's loop, there's only 2 different memory regions being accessed during the particle advance, and the cache has no trouble keeping up with what we're doing. We're very nicely matched to what the capabilities of the memory subsystem are of our platforms. To go into some more details here, our position representation is as mentioned before, the voxel index plus offset. And so instead of saying, hey, here is some global coordinate system with respect to everything is measured, instead we'll just say, look, a particle is in this voxel, and he has an offset with respect to the center of that voxel of dx and dy. As a result, when it comes time to figure out what fields do I need, it's trivial. It's just right there in the particle. If I need to figure out what I'm doing on, say, an irregular mesh code, it makes my life easy. So instead of having to try to figure out on some irregular mesh and do some nasty algorithms to figure out where you're located, again, you're just being told directly. But the only drawback of this thing is that it requires, when a particle crosses into a new voxel, is that you need to transform the offset coordinate system. But since this is normalized and your voxels are this is basically being given with respect to the normalized coordinate system, this cost is trivial. It literally is just negation of a sign. And you can elegantly incorporate it into your charge conservation current algorithm. The main benefit of it, though, is that the position representation makes single precision possible in codes like these. And to understand this, let's consider a single precision 1D simulation with about 1,024 voxels over the domain from 0 to 1. So this is very idealized. If my particles are just represented as a number between 0 and 1 in terms of their position, what I find in single precision is that their worst case absolute resolution in, if a particle is in voxel 0, he sees an absolute position resolution of about 6 times 10 to the negative 11th, whereas particles in the second half of the simulation see a different resolution. It's about 6e minus 8. It's pretty coarse, actually. If we go to the representation I just gave, what we find is that everywhere we have a 3e minus 11 resolution. We actually get an extra bit by using the sign bit to encode some information as well. And this is great. This is great because we don't have any numerical anisotropy within the code. So Emmy Noether is very happy because we obey a lot of symmetries that are inherent at a bit level in the physics of our code. Likewise, we're better everywhere than absolute coordinates by several orders of magnitude in most places. So this is just critical if you want to start using things like single precision within a code. We also sort the particles. Here are some old measurements I actually made of performance back when I was a grad student on an old P3800. What we basically find here is the rate that a 2D, 2V electrostatic simulation I wrote, just a toy to kind of demonstrate this impact, and looking at its performance as we varied various parameters. So along this axis, we have the number of mesh cells. Along this axis, we have the number of particles per cell that exist within our simulation. And we find over here are trivially small simulations, that everything fits within L1 cache, and the simulation's really small, really fast. But as we get more and more mesh cells and this data can't fit in cache anymore, performance suddenly drops when we start seeing the impact of the L2 cache, and then it really starts to roll off. And we see even back here, these measurements are now about 12 years old. Even back then, data flow optimization could make about a factor of 2-fold impact on your code performance. If you sort your actual particles, what you actually find is that the code essentially, regardless of size, always acts like it's running out of L2 cache, unless, of course, it's trivially small and fits within L1 cache. Sorting particles also has another side benefit, and this is something VPIC is getting into now that we have new collision models installed. But when you have collision models for particle-particle interactions, you need to be able to find particles nearby each other, and having particles sorted makes this also a trivial operation. So particle sorting not only gives you a performance kick, but it also allows you to do lots of tricks when it comes to installing various types of particle-particle interactions. So I also mentioned that we do single-pass processing for our particles. And so that means our inner loop conceptually looks like this. For each particle, we're going to interpolate the fields. We're going to update the momentum. We're going to update the position. We're going to accumulate the currents. And then we'll do some fix-ups here to say, hey, did we have anything weird happen to this particle? Do I need to send it to a different node? Did it interact with one of our boundary conditions or whatnot? But this is where everything lives within this loop. And as a result, every particle is touched the minimal number of times during the simulation. Additionally, we store our particle data contiguously. In fact, in the code, the particle looks like this. It's just a triple of floating point numbers representing the offset within a voxel, as described before, the voxel index, and then also the normalized position and charge of that particular particle. This fits nicely within memory. It's all compact and can be loaded very, very efficiently as we stream through the particles. Like I also mentioned, for the field interpolation, we don't access the field data directly while we're integrating the particle. Instead, for each voxel, we compute a set of interpolation coefficients. So here we see the 4 interpolation coefficients necessary to interpolate the X electric field and the 4 interpolation for the Y, and so forth for the other various type fields. And they're laid out in a nice SIMD compatible for these 4-vector machines. And that's just great. Again, our cache has an easy time accessing this. They're all nice aligned in memory and nice and contiguous. And because our particles are sorted, our coefficients are accessed approximately sequentially, large aligned transfers. Now, the only real drawback of this is that this actually requires about 3 times more storage necessary than the raw fields. Now, storage is effectively free. Storage corresponds to transistors on a DRAM chip. Transistors are free. The main impact of this, though, is to make our memory transactions far lower because we're making more efficient use of our cache. Likewise, for our current accumulation, determining the voxels through which a particle passes varies from particle to particle. One particle might remain in the voxel it started. The next one might cross through several. This makes life very difficult if you want to start vectorizing your code. In order to vectorize this in VPIC, we exploit the fact that VPIC is a relativistic code and particles can't move that far per time step. So VPIC makes the initial assumption that, hey, if I have 4 particles, I'm just going to assume none of them cross a boundary. And it tries to push them making that assumption. If it, during that push, it realizes, oh, particle number 5, or sorry, not 5, particle number 2 crossed a voxel boundary, it will then process that guy separately under the hood. Likewise, the interpolation coefficients, instead of making the current contributions directly to the array of currents, we make the current contributions to a contiguous aligned set of partial currents, which we then post-process into the current after the loop. And that means that we also have the same benefits that we saw for the interpolation coefficients. Last main feature, well, there's one more main feature I'll get to in a second, but the second to last feature here on VPIC is that we don't do any of the irregular processing that occurs in the code in the main loop. So if a particle hits an exceptional boundary, for example, it might need communication to a neighboring node, it might need to be absorbed, it might need a refluxing boundary condition, whatever. We don't handle it here. When it hits that boundary, we just make a note of it in a separate stream, which we call the exception stream, and then afterwards we process it in slower application-specific code. This is good because we don't have to pass through our particles to find particles that might have landed in a ghost cell or particles that need additional processing that's already pre-recorded for us. And likewise, it's good because almost always your application-specific things, if you're doing a magnetic reconnection simulation, if you're doing a simulation of laser-plasma interaction or whatnot, these are generally slow, they're application-specific, but now they're cleanly separated from your high-performance loop. You've nicely modulated the high-performance parts of your code, and you can keep this part nice, high-performance in general while maintaining flexibility. Another advantage beyond this modularity is that exception processing doesn't flush out your instruction caches of your processor while the particle advance is running, and so it will also save you a little bit on performance there as well. So in order to exploit four-way SIMD, something I wrote in VPIC and then I've also then exploited in codes like Desmond in my day job, I wrote basically a bunch of wrappers which encapsulate the four-vector SIMD. This is actually a fairly frequently a fairly frequently done approach. But what we find here is, for example, if I want to interpolate the electric field for the next four particles, the actual code in VPIC looks something like this, where there'll be an operation which will describe a memory access pattern. And here it will basically say load a 4x4 matrix and transpose it as you're loading it. And then after you transpose it, for these now four X electric fields, do the interpolation. And this allows us to take VPIC, run it on platforms like Cell, which has four-vector SIMD, run on platforms like x86, run it on platforms like AltaVec, without having to change any of our loop. This will get translated under the hood into the right assembly language for that platform. The last thing I wanted to mention is that VPIC is an unapologetic user of single precision, and that's because the advantage of doing so is too great to ignore. Why? Because we end up moving half the bytes, and we can exploit the fact that there's wider SIMD on these processors. Now, this is safe typically because the discretization error is far, far greater than single precision arithmetic error. As a result, single precision is okay if very carefully implemented. And to give you an example of that, as I mentioned before, like the position representation, if you did a conventional representation of your positions in single precision, you'd find all sorts of weird numerical artifacts within your code. And that doesn't mean that we're religious about single precision. In places where it doesn't matter for performance, in places where there are already existing techniques for cleaning up arithmetic errors, for example, martyr passes for doing divergence cleaning, we use those as necessary. And we've also done extensive convergence studies with theory, experiment, and other double precision codes. In fact, VPIC is stabilized to the point where each voxel has identical numerical properties regardless of how our voxel mesh is translated, oriented, or reflected in the global coordinate system. And so this, again, goes to nice symmetry properties and good numerics under the hood. And make a little preaching here from the soapbox. An attitude I often see from compiler writers, hardware designers, and also in other areas, people assume that if you're using single precision that you just don't care about arithmetic error. The actual opposite is true. If you're in single precision, you care far more about arithmetic error because unlike double precision, if you ignore it, it will lead to catastrophes. And if you look under the hood of CPUs, processors, GPUs, whatnot, they often take shortcuts, particularly in single precision, and I've lost too much hair over it. So to go into a little bit more detail about the hardware for VPIC, we'll give some overview of the Roadrunner supercomputer. First, we'll talk about the hardware description, give some of the considerations in terms of porting a code like VPIC to Roadrunner, and then some of our measured performance. So the workhorse of Roadrunner is the Cell Broadband engine. And the Cell Broadband engine, if you were to look at the die, looks something like this. There is one general purpose core called the power processing element, which is right here. And then there's 8 special purpose 4-vector SIMD cores. And so these guys are really good at doing operations on 4 floating point numbers, single precision at a time. The main thing which distinguishes Cell from a conventional multi-core processor is, well, I guess there's 2 things. One, the PPE and SPI are different kinds of processors. So this one has a different instruction set, different programming style from, say, this processor right here. The other real distinguishing feature is that the SPIs don't have a cache. If you look at the PPE here, there's an L2 cache, there's an L1 cache that it can talk to quickly. But if you look at the SPI, there's no cache. Instead, there's this local store right here. This local store, it's as fast as cache, but you have to manage it yourself. So you get the fun of writing cache protocols when you program Cell. Now, this is actually a very good thing because your cache protocols are designed for general purpose computing. They're not designed for you. If you go through the effort of doing this, you can make your code very, very efficient. But it also means that you have a lot more work to do when you write this because you can't just say load some memory. Instead, you have to coordinate all of this data motion yourself. Now, if you take 4 cell chips and you put them into 2 IBM QS22 blades, and then you hook that to an IBM LS21 blade, which has 4 Opteron cores in it, you get a Triblade compute node. The main feature that's relevant to porting VPIC to this, and also for a lot of other platforms, is that the data path from cell chip right here over to the DRAM over here on the Opteron has about a 2 gigabytes per second bandwidth, whereas if I actually look at the data path right here, it's about 25 gigabytes per second. Now, if I take 180 Triblades and put them into a rack and hook them up to a 288-port InfiniBand switch, I get a connected unit, and that's actually a pretty good supercomputer by itself. But then if I take 18 of those and then hook that into 8 second-stage InfiniBand switches, I get Roadrunner. In aggregate, what you find is that there's about 13,000 Opteron cores with an aggregate performance of about 1/10 of a petaflop in single precision, and also 13,000 cell chips with an aggregate performance of about 3 petaflops in single precision. Now again, and I already pointed this out on the Triblade slide, when you're porting, most of the compute resides on these SPI cores. And the bandwidth between the SPI and cell DRAM is over an order of magnitude greater of that between the SPI and the Opteron DRAM. But to get data between nodes, it's the same. Here you're limited by your InfiniBand networking card. So our strategy in porting VPIC was to flatten Roadrunner. We just would do all of our calculations on cell. All of our data would be stored in the cell DRAM, and the Opterons would relay cell communications in I/O. Effectively, the Opterons are vestigial. We would just be just as happy to run VPIC without any Opterons at all on a machine like Roadrunner. This was somewhat inhibited by the fact that the design of Roadrunner didn't really anticipate this programming model, and physically the cells can't communicate directly. I can't say MPI send on this cell and have it appear over here. So one of the things that we did was to write a little library which actually emulates all of this hardware link and hides it all from you, so that porting and programming Roadrunner is a lot like programming a conventional big cluster. This means that we now have to worry about our particle advance. And in our particle advance, what we find is we have 8 SPIs, we have a bunch of local particles that are located in the cell DRAM, we want to push them. We're just going to divide this up uniformly amongst the 8 SPIs and maybe have a couple leftovers that get handled by the PPE. And then we're going to program the DMA controller on cell to stream through at 512 particles per time this memory, bring in a group of 512 in the local store while we're processing the current group and while we're writing out the previous group that we just processed. But the real heart of it all is handling the random access which occurs within the SPIs. Again, this is a PIC simulation. We need to interpolate. The particle will come in and say, I need fields from this voxel. In order to do that, we need to do random access, and SPIs are terrible at random access, so we wrote our own cache protocol. What we have in this software-managed cache protocol is a 512-line, part read-only, part write-back cache. It has a fully associative protocol, which means that any one of these entries in this cache can hold any data from any voxel in the simulation. And it has a least recently used policy, which means that as we bring in new data, we'll kick out the oldest data that's in the cache. This is nice, these two combined, because it gives us a very strict mathematical guarantee as to what's in the cache. Specifically, the last 512 unique requests I've made to the cache are guaranteed to be in the cache, which means we can write a very simple API for doing all the random access, which runs very, very efficiently. What we do is a new particle block is ready to be processed. We call cache fetch on all 512 particles. Most of them are already in the cache because we've sorted our array. It's already nice and organized. And DMA transfers get started by the cache for any guys who missed. Now, the cache fetch will tell the caller, hey, which lines actually hold the voxel's data. Then, after we've called on all these 512, we tell the cache, tell me when you've done all your transactions, and I'm good to go. I have all the data I need. Now, this is pretty non-trivial under the hood. In fact, most hardware designers think it's too prohibitively expensive to do a fully associative cache, but it actually makes life very easy, and you can do it in fast O1 operations in software, and this mathematical guarantee just makes life so much easier when you're having to deal with this. So now we actually have our data in hand, we have our particle, we're ready to process it. How do we actually process it? Well, we took our original 4-vector SIMD kernel, we unrolled it, and modulo scheduled it by 4. In order to process particles 16 at a time. And so conceptually, it'd be something like this. Over here, we have our particles in the local store. We have 16 of them, and 4 of them will be processed by one of the floating point units on the SPI, and the next 4 will be processed by the second floating point unit. And these are pipelined, and they can overlap instructions, and so then this next batch will fire off at the same time. In fact, we would have unrolled even further if we could, but there were some architectural limitations to how the cell processor worked under the hood. And also, you start running out of memory and registers and all sorts of other things. But overall, what we find is that we get a SPI kernel that operates exclusively out of local store, with most of the SPI registers used, most of the local store used, all of the DMA channels on the SPI used, with most of the DMA transfers overlapped with computation, with many independent SIMD instructions in flight, giving the processor and the compiler lots of ample opportunity to optimize the code, and very few DMA transfers per particle in aggregate from all the techniques described previously. So what does this actually mean? Well, it means that if I look at the kernel performance, we find that if I was to run VPIC on the cells, I get 162 million cold particles advanced per second per cell. Cold particles advanced per second. Cold here just means the particles didn't do anything exciting during the particle advanced. Versus if I was to run on the Opterons of Roadrunner, 10.3-fold speedup. And so that means we got a 15.7-fold speedup by exploiting the SPI here. But this is not quite a fair comparison because the SPIs run at a 1.8 times faster clock speed, and there's 8 times more of them. But even after taking this into account, we find that these transformations allowed us to get a 1.1 clock-for-clock speedup in spite of the SPI's minimalism. I mean, it's kind of barely difficult to call it a processor. And the fact that VPIC was already pretty much a hot rod on running on conventional platforms like x86. And if we then just extrapolate out with our floating point figures, what we find on the whole of Roadrunner, we can get a little bit over half a petaflop sustained at pushing particles. And if we were to run on Opterons, we would need about 200,000 cores to achieve a similar performance. And this actually gives some motivation as to why hybrid computing models are starting to take over, which is that for a lot less silicon, for a lot less chip, you can get a lot of performance if you take the effort to exploit it. So this means we get to play Amdahl's whack-a-mole. We sped up our particle advance by 15.7, and Amdahl's law teaches us that the rest of the code becomes relatively more costly. So if I look at a lot of VPIC runs, what we might find is that 96% of the time we were spent pushing particles, and 4% of the time we were solving fields and doing diagnostics and the other little bits of the computation. If I then apply this to Amdahl's law, what we find is that this 96 gets divided by about 16. It becomes 6. We get an overall speed up about tenfold. But what you'll find on platforms like Roadrunner and on GPU-accelerated platforms and so forth is that they don't obey Amdahl's law. They obey Amdahl's street justice. And this is because the rest of the code is absolutely more costly. And this is because the general-purpose compute resources tend to be less powerful in order to make room for these high-performance compute resources. So if I look at the PPE, compared to an Opteron, the PPE is 2 to 3 times slower than the Opteron cores at the stuff VPIC does. So instead of getting this 16-fold speedup, what we might actually find in practice is only a 5 to 6-fold speedup because the other parts of the code got so much slower. And this also leads to a lot of problems that you get when you start looking at porting and dealing with these higher-end platforms, which is that the end-to-end performance on these is far more sensitive to the unaccelerated kernels, the places where you are lazy in your code, than on conventional platforms. For example, in VPIC, we needed to accelerate our particle sorting process. It was the next most expensive thing. And then we've also had to accelerate lots of the field advance in order to try to keep the overall acceleration beyond an order of magnitude, which is kind of where we want to be. I mean, several-fold is good, but tenfold is cool. Likewise, actually what we find in VPIC now, and this is kind of a bigger problem, long-term, that you'll find on a lot of platforms, is that our Amdahl bottlenecks are now actually cropping up in the one-off user-provided application-specific diagnostics. So VPIC users will say, look, I'm doing this kind of simulation. I want to look at trapped electrons in this wave. And they'll write up a basic diagnostic. We install it. Then all of a sudden, the code performance drops because their code ends up being the bottleneck, whereas on a conventional platform, it would have been in the noise. Now, to an extent, a lot of this, it's usually not hard to make these a lot faster, but there's going to be some time while user experience and the development model stabilize to really start avoiding these problems. There's no real silver bullet to those. So overall, our end-to-end performance, and this is what we showed at Supercomputing last year, we used 2 simulations and a laser plasma interaction parameter study to benchmark the weak scaling. And what we found overall is that we got the same physics. We got it 10 times faster. We had 2 LPI science problems, and this is just scaling out. At the farthest out data point, we were doing trillion particle simulations at about, actually, we're currently over 0.4 petaflops for sustained end-to-end performance, but at the time, they had a faulty DRAM in one of the connected units, so we could only do 17 then. But so You can scale, you can do lots of big things. So what is this all good for? Let's talk a little bit about the science that's being done with VPIC on these kind of petascale resources, and then I'll give some thoughts as to what might go into looking at, say, like a gyrokinetic code and what it might take to exploit modern petascale resources on it. So one of the areas which VPIC is getting a lot of active use on Roadrunner is in inertial confinement fusion, and I imagine with this audience, most people know what inertial confinement fusion is. The main thing here for VPIC is that laser-plasma interaction is a fairly major issue in this. And this is because laser scattering means that the DT pellet could get too little compression. Likewise, laser scattering means compression can be asymmetric. And also, if there's a lot of laser-plasma interaction, it can preheat the electrons, making it harder to compress the pellet. And the multi-billion-dollar question of all of this is, what's the risk posed to a system like Livermore's National Ignition Facility by LPI? And petascale supercomputing is being used to address this issue. So over here, we have Nano VPIC modeling doing the microscopic physics of laser plasma instabilities. This was actually the inaugural cover of Physics of Plasmas when they started doing images on their magazine. And then that can be used to develop models to put in codes like Livermore's PF3D laser modeling code, which then can in turn go into hydrodynamic modeling codes like Livermore's Hydra. And there's a really nice example already of computational science in action for this, which is that if we look, stimulated Raman scattering, there was a nice linear theory developed by Drake in '74, but in experiments at the Trident Laser Facility, there was unexplained behavior observed. And what the linear theory predicted was essentially this nice, smooth, just basically linear plot. As you increase intensity, how much light would be reflected by stimulated Raman scattering. But what they actually found when they did experiments and measured it, they found that there was a low intensity where there was a sudden sharp onset, and then there was a plateau in here. And no one really understood what was going on here. So in VPIC, it identified the key physics, and it required us to use petascale resources and looking at the kinetics and everything that was going on. It turns out that plasma wave bowing, self-focusing, filamentation, and trapped particle modulational instability caused this rapid onset and saturation. And then we also got nice agreement with experiment for the reflectivity we measured out of our simulation. And then in kind of a classic example of how computational science works, these insights lead to nonlinear SRS theories. You can look up these papers if you wish and read more about it. And now VPIC is being used to understand and predict LPI and how to mitigate it on machines like NIF. There's an even more interesting example which recently came out, which is we've been looking at laser ion acceleration processes, and one of the mechanisms is to do short pulse laser ion acceleration. And so here you basically have a thin foil at solid density, and as a result, the electrons, if you treat the electrons as not bound to the nuclei, this is far beyond the critical density for the laser frequency coming in. And if you shoot a laser at it, people noticed experimentally that they'd get these nice monoenergetic beams being accelerated out in the hundreds of MeV. And so VPIC wanted to understand this process, and we did a bunch of simulations with it, and we corroborated that and the mechanisms that were proposed. But we also discovered in playing around with the parameters that relativistic effects would actually make the foil transparent if the pulse had an extra high contrast such that the pre-pulse didn't destroy the target, and also increase the intensity and use the thinner foil. And this relativistic effect allows the pulse to break out and give an extra acceleration, and this was published in 2006. Now, again, in the kind of typical way, you have some insights from simulation. You can develop new theories. One such example would be if you have a linear polarized light, you can get a relativistic Bunemann instability that can give you this extra acceleration. But the more interesting thing is that this prediction drove a redesign of the Trident Laser Facility in order to be able to measure this effect and see if it actually occurred, and that this prediction was actually confirmed, and this is now in press at PRL. And should be out very shortly. And here's just a nice picture of circular polarized, which is has a slightly different mechanism for doing the extra acceleration on the breakout. So now to talk a little bit about what if you have an existing code, or if you're planning a code for a particle type method, and even if it's not a particle method, what might you want to do, and what are the pros and cons of it? Well, first, a lot of the optimizations already talked about apply. Use single precision aggressively. And the pro behind this has already been iterated, but I want to hammer on it some more, is that you end up moving half the data and you have wider SIMD available to you, double the width that you have available to you in double precision. The con of this is it requires great care for robust implementation. If you don't want to take a lot of time developing your code, write it in double precision, you probably won't have to think that hard about the implementation. If you write it in single precision, you will have to think very detailed about the numerics and do a fair amount of analysis and error propagation and so forth to make sure that your code will not be producing junk. The next is you want to touch your data as minimal times as possible. In our particular case, we wanted to do this monolithic particle advance. And this is because it minimizes the amount of data streamed to and from DRAM. The drawback of this is that it's harder to modularize code, and if you have an existing code which is written in these tiny modules, it's a fair amount to retrofit an existing code because you're rewriting basically your physics loop and how it is, appears to the outside world. One compromise that you might want to look at doing with these is to cache block your particles. Essentially say, look, I will, instead of advancing all my particles at once, I will do small chunks at a time and do all my separate passes on the small chunks to hopefully get some impact from the cache. Likewise, if you're doing a particle simulation, I strongly recommend voxel offset particle positions. There are just so many pros to this because, one, your arithmetic error drops several orders of magnitude, and that's essentially required if you want reliable single precision. You can get faster field interpolation, you can get faster particle accumulation, you can get faster particle sorting, you have better handling if you're on an irregular mesh type code. The biggest con of this is that it's difficult to retrofit an existing particle code because now you're changing what a particle looks like and everybody touches the particles. Likewise, you want to sort your particles aggressively, and this is good because now you've improved your memory access temporal locality. And temporal locality is just a way of saying, hey, when I access some region of memory, I'm likely to access it again a short time later. The big con behind this is that, and this is not really a con, but if you are not using the technique I mentioned before, the particle representation, determining where you are on the mesh, which is your sort key, can be expensive, it can be difficult, and it can take a while. And another thing is that sorting, particularly on multi-core processors, is kind of tricky. And in my SIDAC paper, which just came out, which is basically on what this talk is based, there's a nice description of some multi-core friendly particle sorting algorithms. Again, you also probably want to use SIMD-friendly array of structured data layout. So here you want to be worried about, is your data aligned in memory so that the CPU can stream it efficiently? Is it aligned such that you can do these vectorized operations efficiently on it? Again, you get better spatial locality. This means that the data you're accessing is near each other, so your cache can help. It also means that you can start using SIMD, and that can give you, maybe a factor of 2, maybe in limited cases a factor of 4 speed up on your code. Again, this is also difficult, though, because here you're talking about reorganizing your fundamental data structures, and if you pick those wrong when you first designed your code, you're kind of stuck with it. Actually, again, to preach my choir, Fortran encourages the wrong style of data for modern computing. Another thing is that you often will want to make approximations where you say, look, in our particular case, we assume our particles are cold, they don't do anything exciting, and as a result, we can vectorize that. And so you want to find a common case within your code. You find that common case, you optimize that. Now, that common case will be physics dependent. And so as a result, depending on the physics you're doing, it might not be common enough to be worth exploiting in the cons. The wider SIMD architectures also are starting to change things. Here's another area where if you look at a GPU, effectively it's like a 16-way vector processor instead of a 4-way vector processor. Intel, likewise, has wider vector chips in development. And so, this cold might not be sufficient in 5 years. But again, you have to always think and know what you're going to be running on. It's also good to consider, this is a kind of a specific case of the more general rule. As I showed earlier, memory access is far more expensive than floating point access, and likewise, as a result, it's often cheaper to replicate data and computations if you can get away with less transactions by doing it. And one of VPIC's optimizations is to use an interpolator. So here, we pre-compute a bunch of per voxel interpolation coefficients before the particle advance. And the advantage of this is it's a faster interpolation, especially if you're doing an irregular meshed code. It also gives you improved memory access spatial locality. The disadvantage of this is that you have a potentially prohibitive memory footprint. If you're really interested in doing something like a fourth order particle mesh AWOLD type method, then you might find that the interpolator still doesn't fit within your DRAM. Even though it'd be faster, you just can't fit it into memory. This also doesn't work if you're doing a simulation which has less than 1 particle per voxel. That almost never happens in the simulations our users use, but there are certainly simulation domains where they're using particles as tracers or whatnot, and here you're essentially relying on the fact that there's multiple calculations per voxel to be done with that interpolator to amortize this cost of forming the interpolation coefficients. This is basically the same thing I said on the previous ones. You probably want to, again, just look at where you can replicate computations in order to save on memory transactions and data movement. And also, this goes back to the case of the rule before, finding a common case within your code. You want to use an exception list and essentially extract out the part that really needs to be high performance, the part that's general, and really hammer on that, and then have all the other stuff processed essentially offline in slower code. It will make your code easier to maintain. It will make your code faster. The kind of con behind this, at least with respect to VPIC, is that some costs for kind of simulations we've looked at, for example, if you're looking at things such as like volumetric ionization processes of particles within a material medium due to field strength, you might have a volumetric scaling exception cost, in which case this might not be a viable strategy. But most exceptions scale as the boundary surface area of your simulation. This one is kind of opposite of the old advice. Most people thought charge conserving codes were always prohibitive because you have to walk the mesh, and walking the mesh is fairly expensive. But nowadays, this is kind of reversed because, one, you get improved physics accuracy by walking the mesh. It also can make your life easier when you have to figure out where particles are on the voxel because you're exploiting the previous information of where the particle was if you're looking at things like an irregular mesh. It's also good because when you have complicated boundary conditions, for example, simulations with complicated materials or walls or whatnot, this can give you robust particle boundary hit detection built into your loop. The main drawback is that if you're doing physics, which requires particles to pass through many voxels per step on average, then you might not want to look at charge conserving, maybe make a different approximation. Likewise, there are some interesting algorithmic techniques if you're on an irregular voxel mesh that can kind of obviate the need for this. There are some other optimizations that we really haven't discussed yet that can also be useful. So one thing people often like to do, particularly if they're like looking at like a tokamak simulation, which has a fairly complicated geometry in terms of what the walls look like and so forth, they'll want to do like curvilinear boundaries that are boundary fitted. But this is fairly difficult to code, fairly expensive to develop. Something that is a nice alternative and often applicable is to use cut cells to optimize this. And this is good because, one, it's a little bit easier. It's better understood numerically. They're easier to optimize than irregular mesh. There are some problems that are outstanding. For example, there are a lot of 3D problems in electromagnetics where cut cells are, I think they're mostly solved now, but still, I mean, there's various edges, various approximations that, might not be acceptable. In fact, here's a simulation I did with a postdoc of mine when I was at Los Alamos. This was just a H- gun, so you essentially have electrons get boiled off, they ionize an H gas that hits this molybdenum converter, and you get accelerated by electrostatic fields and focused and launched out. This is used at the Lance particle accelerator facility. And they were looking to see how do they increase beam current, what's actually going on in their device. But the main feature here is you actually do have, and you really care about the focusing, you really care about getting the normal electric fields, having a curved boundary. We did it with cut cells. You have a nice curved boundary here, even though this was still using regular and it ran very efficiently. This one's slightly more technical, but often you might not even want to consider doing kind of a usual, let's index along X and index along Y and index along Z. You might want to consider indexing your voxels in a strange fashion. A common scheme is a Hilbert space-filling curve. And this can improve your temporal locality. It depends on the kinds of things you've done. I've experimented with it in VPIC on Roadrunner. I got some minor gains from it. I don't know if it was worth the complexity cost, but there are a lot of domains, particularly AMR codes, adaptive mesh codes, really love to do techniques like this to figure out what's the way to traverse their meshes. It's a little bit tricky to implement, it can make your life a little bit harder when you're trying to figure out where particles are on the mesh. That's about the only real drawbacks of it. Another one, and this one is kind of particular to gyrokinetic pick, but there is a general broader rule here, which is that elliptic equations are generally a bad idea on high-performance computing. Poisson equation being the textbook example of an elliptic equation. And the reason why is that information in an elliptic equation must propagate from each node to all the nodes every field advance. This is a consequence of having a 1 over all force law. As a result, if you're doing any kind of code with the non-local elliptic flavor field equations that assume the speed of light or the speed of sound or whatever is appropriate for your physics is effectively infinite in order to generate a Poisson's equation, you'll end up with an elliptic system. But this means that you have to do very expensive communications within your code. If you're doing a regular mesh, you might do it with an FFT-based method. If you're doing something like an AMR code or some of these other meshing strategies, you'll essentially end up with like trees, which you'll find in a multipolar, multi-grid type method. And in the end, because you're doing communication where information is going from all nodes to every other node, you kind of run into scalability limits, and this gets tougher and tougher to do as more and more compute gets thrown at you and less network gets thrown at you. So something that I've experimented with both at my day job and elsewhere is that often you can recast your elliptic equations in a hyperbolic form, which for the speeds much slower than the slow speed of light you've put into your code will still generate the same physics. And if you use this like slow speed of light, for example, if I'm running Maxwell's equations and I'm interested in looking at thermodynamic properties, what we'll find is that the Poisson-Boltzmann system and the Maxwell-Boltzmann systems both model the same phenomenon for stuff that's slower than the speed of light. In fact, they even have identical partition functions after you integrate over the radiation degrees of freedom. So this is one of my speculations I made to the PPPL group, just saying, hey, maybe if you could recast a lot of your elliptic equations in a hyperbolic form and use some of those, you'll be more friendly going forward onto bigger resources because you'll be better computationally matched the resources you're given. So to give some conclusions here, and then there's a lot more slides that follow this, which can go into a lot more numerical details for people who are interested. But the main thing here is that petascale supercomputers can change the way we do science. But tapping this potential requires we rethink codes and analysis, because data motion is not free. And the main reason for this is that supercomputers are getting faster, but not the speed of light. In fact, what you really want to do from a software optimization standpoint is you want to optimize your code for data flow, and this actually future-proofs it. When I was at Los Alamos, and this would be about 8 years ago, was when I wrote VPIC, the core of it, I data flow optimized it then, and then when Roadrunner came along and they asked if Roadrunner would be good for this platform, I didn't need to do any major changes to it other than porting over the kernel for the particle advance and doing all those transformations I showed you to get those order of magnitude speed-ups. The other thing is that Roadrunner, it's a hairy platform because you have heterogeneous compute. You have to do a lot of thinking about your data flow management, but that's going to be the future, whether you like it or not. And in the future, what we're going to find is routine petascale computations. In fact, right now, for about $100, you can buy a teraflop on a GPU, put it under your desk. So, petascale is actually getting pretty affordable if you don't mind programmability of your platforms. Likewise, expecting 100,000 core parallelism will be fairly routine. Heterogeneous cores are coming. Heterogeneous cores are coming because that's the way they manage the power. And intermingled compute and memory, and that's because the speed of light isn't fast enough, and so you're going to see these complicated memory hierarchies. You're going to see lots of cores for your transistors. And to actually exploit these platforms to get good performance, the data flow optimization will be paramount. So this is basically the boilerplate here. This research was supported by the LDRD program, the DOE, the NSF, and NASA. The IBM Roadrunner team gave us some time when Roadrunner was at IBM's Poughkeepsie facility in New York for early testing. And I got some help with these slides from Ken Koch, Wee Lee, Jerry Margulies, Eric Nelson, Tian Kai Tu. And a lot of the visualizations you saw were done with the Insight Gold software. And if you want to start learning about all sorts of fun, scary things on how the numerics works, then we can talk about that as well. Any questions?